Armungam Thami Javed.
Yes.
He's from Tata Institute of Fundamental Research, and he's going to talk about crystal growth pathway to quantum materials, side and side. So I will give you hands-on 5 minutes.
Okay, sure. Thank you, Chairman. So, good afternoon to everyone. I hope after a good food, you wanted to have a good nap, but I won't allow you to sleep. So, I'll make you listen my talk for the next 30 minutes. Okay, so since this is a session on advanced material synthesis and characterization, I'm going to talk about the crystal growth aspects, how we have grown some of the crystals, see mainly the silicides and pnictides. So I have chosen these two things, silicide and pnictide, because most of the silicide have very high melting point. Very high melting point in the sense that they have a melting point greater than 2000 degrees centigrade. So if a compound has a very high melting point around 2000 degrees centigrade, how do we grow these crystals? See, one of the ways is to use a flux and to dissolve it in some solvent. And most of the silicides, they don't dissolve in most of the common solvents. So in that case, even if you're using a solvent, then you may be incorporating some impurities into your crystal. So if you want to have a high quality single crystals, you need to grow these crystals directly from its melt. So I'm going to explain to you how we were successful in growing some of these two binary compounds, particularly of very high quality. And I've chosen the other compound series, pnictides. So pnictides have high vapor pressure. See, most of the pnictides have very high vapor pressure. So we need to take some proper care to grow these kind of pnictides. So we have grown these crystals of pnictides by flux growth method. So basically, I'm going to concentrate on two different crystal growth techniques. One is Czochralski method. The other one is the flux growth method. That is a high temperature solution growth method. So before I proceed, I wanted to acknowledge some of my students and postdoc. So these are my former students who have completed their PhDs, and Dr. Shovandan is a postdoc who is working in my lab, and Ruta Kulkarni is a scientific officer. So some of the first principle calculations, electronic structure calculations, have been done by Dr. Bahadur Singh. Okay, so before I proceed to this actual main topic, I just wanted to highlight what is the research focus that we are doing in our lab. So TIFR, as you know, has been working on the strongly correlated electron system, particularly the rare earth-based magnetic systems, quite long, for more than 4 to 5 decades now. And I'm continuing the legacy. I'm growing the single crystals of cerium-based compounds, ytterbium-based compounds as single crystals and study their physical properties, anisotropic physical properties. So cerium and ytterbium-based compounds are quite interesting because they have these competing interactions, RKKY and Kondo interaction. So which can be these, the magnetic ordering in those cerium and YB compounds can be tuned by varying this, by applying a pressure or magnetic field or dopant concentration, and we can tune them to quantum critical point, and we are seeing this various interesting physics at the QCP. So this is one of the aspects that we continuously working on these rare earth based intermetallic systems. So other thing is that when pnictides came into action, so we just did lots of work on these pnictide compounds, and one of these interesting compounds we studied is calcium Fe2AS2. So we have constructed a phase diagram from our transport measurements and inelastic neutron diffraction experiments, and we have found out that the spin density wave decreases with the nickel concentration, and for a particular concentration of nickel, we find that the superconductivity and spin density wave coexist. So this phase diagram has been constructed by us. This was a work done long back. So and also, we work on charge density wave systems. Like for example, this lanthanum platinum to silicon 2 is a charge density wave system. It exhibits a charge density wave at around 70 Kelvin, and also it shows superconductivity. So we have grown these single crystals, and we have studied the anisotropic physical properties in this. Apart from that, nowadays, our focus is on topological materials as well. So we study the semi-metallic systems which show some interesting physical properties like large unsaturated magnetoresistance, Shubnikov-Dihas oscillations, and DHP oscillations to study the Fermi surface properties. And in all these cases, the band structure calculations were done in collaboration with Dr. Bahadur Singh, who is our junior colleague in our department. Okay, so all these works we do only on single crystalline samples. We don't work on polycrystalline samples. We grow the single crystals and we study the anisotropic physical properties. And for this, we employ the various crystal growth techniques. Like for example, this is the Zakralski method. See, Zakralski method is you just melt the compound, insert a state crystal, and you can pull that. And typically, the Zakralski method, people use a conventional resistive heating furnace or induction heating furnace. But here, we are taking advantage of this arc melting, and we use 4 electrodes, tungsten electrodes, and we melt the sample. So in this case, we can grow single crystals whose melting points are as high as 3000 degrees centigrade. So that means high melting samples can be grown using this tetra arc furnace that we have. The other method we employ is the Bridgman method. Some of the materials, they melt congruently. That means we can grow the crystals directly from the melt, but they have some high vapor pressure. So in those cases, we can grow the single crystals by Bridgman method. The idea is very simple. You take the material in a sharp tip ampule, keep it in a 2-zone furnace, and make sure the sample is molten here in the hot zone and slowly translate it. So you can get good single crystals. In this case, the entire chunk will not be a single crystal. You will get large grains of the single crystals. And we do low diffraction to find out the orientation of the crystal, and we cut the crystal for the anisotropic studies. And flux growth, the people who are working the topological materials may know that. I mean, this is a quite often used method. It's a very simple, it doesn't require any hi-fi instruments. You just need to have a box type furnace and a centrifuge. You can grow the single crystals by dissolving the material to be crystallized in some solvent, and you can grow these crystals. So that's a flux growth technique. And the chalcogenides, these are 2D materials. This morning you heard a very nice talk by Professor Arindam Ghosh. So most of the 2D materials are grown by vapor transport. So either some of the material they sublime, so you can take advantage of this sublimation process and you can put it in a 2-zone furnace, you can get single crystals. Sometimes you can use a transporting agent like chlorine, bromine, iodine, things like that, and then you can transport these materials and you can grow the single crystals using this vapor transport technique. And we have an optical floating zone where we can grow single crystals of oxide materials. So we have grown several of these pyrochlores, and we have grown this beta gallium oxide single crystals using this optical floating zone furnace. So these are the facilities that we have in our lab to grow various intermetallic and oxide single crystals. Okay. So having said that there are so many methods available to grow the single crystals, how do we choose which method of crystal growth should I adopt to grow a particular material? So as I told you, if the material is congruently melting, then you can directly grow it from the melt. That means, for example, here this is a silver and neodymium phase diagram. The silver and neodymium, if you take 1:1 ratio, it melts at around 952 degrees centigrade. So if you take it and take it about 952 degrees centigrade, if you take it to 1000 degrees, it's completely in liquid state. And when you cool down, it doesn't dissociate into any other phase. It remains in AgND. So this type of materials is called congruently melting, and you can directly grow these crystals from the melt. So that is why we can use the Zakralski method to grow the single crystals of silver and neodymium. On the other hand, there are some other compositions. It dissociates at 825. For example, this silver to neodymium, it dissociates at 825 degrees centigrade. Suppose if you heat it above this one, take it to its liquid state. When you come down, it doesn't form in Ag2Nd. Instead, it forms in this composition and it takes the composition from this one. So it has a multiple composition. So in those cases, you have to grow these crystals by flux growth method by dissolving it in some solvent. And there are various other things. This is a eutectic point. So that means eutectic is the lowest melting point in the phase diagram. So here, say for silver and neodymium, although silver has a melting point around 960 and neodymium has around 1020, when you take it in the ratio 80:20, its melting point comes down to 640 degrees centigrade. So this is a eutectic point. Sometimes, if you want to grow silver Nd, you can take advantage of this eutectic composition as a flux to grow these single crystals. Okay, so now in my title I mentioned about the silicides. So I'm going to focus on these two silicides, MoSi2 and WSi2. And so these compounds, MoSi2, it melts at around 2020 degrees centigrade, and WSi2 melts at 2180 degrees centigrade. These are quite high temperatures, and we were successful in growing the single crystals. So before I go into the detail of this crystal growth, I just wanted to tell you about why we are interested in these systems, WSI2 and MOSI2. So all these things, the semi-metallic system got attention after this paper by this Ali et al. In Nature in 2014, where he has showed that WTU2 shows a huge, extremely large magnetoresistance, and it shows a large unsaturated magnetoresistance even up to a magnetic field of 60 Tesla or something like that. So these semi-metallic systems got attention, and soon after the discovery of this large unsaturated magnetoresistance, people started working on various systems. Sorry. Ah. So they looked into various binary systems like lanthanum, bismuth, lanthanum antimony, lanthanum, bismuth, these kind of systems, and they have found out that it also exhibits large unsaturated magnetoresistance. These are compensated semi-metals. These means they have equal number of electrons and holes. So when these kind of compensated in these kind of compensated systems, you see this extremely large magnetoresistance, and interestingly, they observed that this electrical resistance increases as you increase the magnetic field, and they show this transition. I mean, there is a metal to insulator kind of transition, and then it just stays there. It flattens out here. So this, if you draw into your phase diagram, it forms into a triangular phase diagram. So this means that this magnetic, this metal to insulator kind of transition, it increases as you increase the magnetic field, whereas the inflection point here, which saturates here, it remains almost flat. So this became an universal triangular phase diagram in these kind of semi-metallic systems. Irrespective of the chemical and structural differences, all of these compounds exhibited this kind of triangular phase diagram. So in this connection, we wanted to look into this MOSI2, which is a semi-metallic systems. When we checked in the literature, only this paper was available in 1986, it was done, and it showed a large magnetoresistance in a field of about 9 Tesla. So we wanted to grow these single crystals, and we wanted to study the Fermi surface properties of this compound. So as I told you, this compound is a congruently melting compound. It has a melting point close to 2000 degrees centigrade, and we have a tetra arc furnace. It's a simple arc melting furnace. Instead of mono arc, it has 4 tungsten electrodes, in each of these tungsten electrodes, we can pass a current of about 100 amperes. So the sample is held in this copper hearth. The cartoon is shown here. The copper hearth is water cooled. We can take about 10 grams of MOSI2, and then we can melt it using these 4 electrodes. And once the sample is molten, we insert a seed crystal. The seed crystal is nothing but a polycrystal cut out from this 10 grams of sample. And once the seed crystal is inserted, the seed is coming from room temperature, whereas the sample is at 2000 degrees centigrade. So when the seed crystal touches the melt, a local solidification happens. And then we have to pull the crystal immediately out at a faster pace, and then we allow, and you can see that once the seed touches the melt, you will see this multiple crystallization which is happening here, and we do a necking process. We allow only one grind to grow into a larger single crystal. So this is how in almost all of this Czochralski growth method, people adopt this kind of necking process to grow a single crystal. For example, this is a polycrystalline seed, and we have tried a small necking here, and during the growth also we performed another necking here, and then we tried to get a better quality single crystals. So this is a photograph taken during the growth. It looks like that. So the melt is at 2000 degrees centigrade, and the crystal is growing here. So it is interesting that we can watch the single crystal growth when the crystal is being pulled. So typically the total mass of the sample is about 10 to 12 grams, and the crystal pulling speed is about 10 mm per hour. So we have adopted about 10 mm per hour to grow the crystal. So typically the single crystal growth of about 7 centimeter crystal takes about a day. If you start at morning at 10 o'clock, by evening 5 o'clock, you can complete the crystal process. Okay. So the next thing is that first thing we did a powder X-ray diffraction to confirm the phase purity, which as you can see that it is completely phase pure. The main point is that we have aligned the crystal along the crystallographic directions using Laue diffractometer. So this Laue pattern confirms that this is along the 100 orientation, and this is along the 001 direction. So we have cut this crystal along these 2 principal crystallographic directions like 100 and 001, and for the physical property measurement. So this is the transport measurement on MOSI2. You can see that the residual resistivity reaches of the order of 7 nano ohm centimeter. So if you calculate the RRR, it is about close to 4000. This tells that the crystal is of extremely high quality single crystals that we have obtained. So this is along this current parallel to A axis, this is along current parallel to C axis. Here, when you apply the current along the C axis, the RRR is about 350. So this is for MOSI2, and for WSI2, the RRR is about 160 here. And you can see that the resistivity for 100 and 001 direction at room temperature, it's of the order of about 10 microohm centimeter. Here also it's about 10 microohm centimeter. So there is a little anisotropy in this one, because at room temperature you see that here also it's 10 microohm centimeter, here also it's about 10 microohm centimeter. So we checked into the literature, and the previous literature also says that around 300 microohm centimeter, 300 Kelvin, the resistivity is completely isotropic, but the anisotropy is observed at very high temperature if you go to higher temperatures. Okay, so we have also observed this from the magnetoresistance. So from the magnetoresistance studies, we have also constructed the triangular phase diagram for this MOSI2. It also follows the same universal triangular phase diagram observed in other semi-metallic systems. And the magnetoresistance is extremely high. It reaches up the order of 2 into 10 power 5 at 2 Kelvin for WSI2. And it is also showing an unsaturated magnetoresistance, indicating that the sample is highly compensated semi-metal. Okay, so the interesting feature we observed is in the Hall effect. So depending on the direction in which we apply the magnetic field, the carrier concentration changes. For example, the blue curve, the magnetic field is applied along the 100 direction. For the red curve, it's along the 001 direction. When we checked into this literature, this was mentioned something as goniopolar effect, which is seen in NaSN2AS2. These are single band systems and which are with an open Fermi surface. But however, ours is not a single band system, it is a multi-carrier system. And this is maybe due to the multiple Fermi pockets which are there in this from the band structure, and the charge carriers with different transport mobility along different directions might lead to this kind of anisotropy in the Hall effect. And we have observed DHPA oscillation signal in this work. We have done an angular dependence of this DHPA oscillation. This was done in Tohoku University. We went there for this measurement and we performed angular dependence. And these are the 3 different frequencies along 2 different crystallographic directions. Based on, see, this is the experimental angular dependent thing, and here it follows exactly the theoretical and experimental matches very well. And from this, we have constructed the band structures. So this is all about MOSI2. Next, I will just switch to the pnictide compounds, calcium copper Sb and calcium copper 4 arsenic 2. So both antimony and arsenic have high vapor pressure. So if you just heat it up very randomly, these are arsenic and antimony, there is a possibility of explosion inside your furnace. So you should take proper care. And so this calcium copper Sb crystallizes in the hexagonal crystal structure, and this is a rhombohedral crystal structure. Both are nearly a hexagonal type, and the A axis is about 4.4 angstroms and C axis is about 8.13 angstrom. And so here the C axis is very long, something similar to your Bi2Se3. So we were successful in growing these single crystals. Okay, so to grow this crystal, so typically in the case of flux growth, you take one of the constituent elements as a flux. The constituent element may be one of the low melting materials. Like for example, if you look at this calcium copper antimony, antimony has a melting point around 600 degrees centigrade, and in principle we can use antimony as a flux to grow these crystals. But the problem is that there is a large possibility that calcium and antimony binary phase may form. So in order to avoid the binary phase diagram, we looked into the phase diagram of copper and antimony. It forms a eutectic around 63% of copper, 63% of antimony and 36% of copper. And we have taken advantage of this eutectic composition. Similarly, for copper arsenic, we have taken advantage of this eutectic composition, and we have used that as in large quantities. That means those things act as a flux to grow these crystals. So we have taken this in a alumina crucible. This alumina crucible is subsequently sealed in a quartz ampule, as these materials are metals, and when any metal, when you heat it to elevated temperature, it will get oxidized. So everything has to be done in vacuum. So this is sealed in a 10 power minus 6 torr of vacuum, and there is a small quartz wool is kept here. So there is a small necking here, and then there is a sealing point. the point, the necking here is done just to separate the crystals. Like for example, the ampule was sealed in vacuum and put up in the furnace, and we have heated it at 30 degrees centigrade per hour to 1050, kept there for 24 hours, and then slowly cooled down to 625 degrees centigrade. So now, how do we separate the crystals? To separate the crystal, we have to take this ampule from the furnace at 650 degrees centigrade and put it upside down in a centrifuge, so that the molten flux, which has a low melting point around 520 and 600 degrees centigrade, these which are in liquid state will get collected here when you do the centrifuge, and the crystals will remain inside this crucible, and we can just gently tap the crucible to get the single crystals. And this is how the grown crystal looks like. So after removing the flux, we get pure single crystals of these materials. And as a rule of thumb, the largest crystallographic direction has the slowest growth front. These are platelet-like single crystals, and you get this kind of hexagonal type crystals. So the first thing we do is that we do a Laue diffraction, and we check whether the quality of the crystal is good. The Laue diffraction spots are spherical, and it confirms the good quality of the single crystals that we have grown. And of course, since these crystals are grown by flux method, the first thing that we do is that we check the powder XRD to check whether the desired phase has grown into a single crystal. So the powder X-ray diffraction, the Rietveld analysis confirms that the grown crystals are induced stoichiometric, and we have used these crystals for the other various anisotropic studies. Okay, so the transport properties here, if the calcium copper 4 arsenic 2, it shows a large drop in the resistivity at around 50 Kelvin. So this is typically observed. This is not a magnetic system, so you don't expect any magnetic transition. But we found that there is a structural transition which is happening. So this may be associated to a CDW kind of transition. Similarly, this is along this, when the current is parallel to the AB plane and the field is along the C axis. When the current is passed along the C axis also, we see a change of slope at around 50 Kelvin. So there is something is happening at this temperature, which we attributed to the CDW transition. So typically in a CDW transition, because of the gap opening, the electrical resistivity increases and then it remains constant. But in our case, this is for the lutetium pyridium silicon 10, which is a famous CDW system, and lanthanum platinum to silicon 2, which shows an increase in the electrical resistivity at the CDW transition. But in our case, the resistivity shows a drop. And this is something similar to what they have observed in tantalum diselenide, where the electrical resistivity drops at the CDW transition at around 100 Kelvin. So they have done a very detailed study using the RPS measurements, and they found out that from the RPS measurement, there is the finite density of states above the CDW transition, because it shows a metallic transition here. So above the CDW transition, there is a large density of states over the entire Brillouin zone. But when the CDW transition happens, there is a gap which is opening, but that gap is not opening perfectly, but there are some patches which touches this, there is a band crossing which is happening at these points. So this, they call it as a Fermi patch, and because of this small touching point, you see a metallic nature of this tantalum diselenide. So we attribute that the similar behavior can also happen in this calcium copper 4 arsenic 2. So we need to do a detailed RPS measurement on these single crystals as well. Okay, so this the transition which is observed at around 52 Kelvin in the electrical resistivity shows a sharp, the heat capacity also shows a sharp peak at this point. So this tells us that even if you apply a magnetic field, there is no change in the heat capacity. So this also confirms that the transition is not any magnetic or something like that. It is simply a structural transition. And there is a huge hysteresis which says that it is a first order like transition. And we have also confirmed from the single crystal X-ray diffraction in the Petra daisy that above 80 Kelvin and below this CDW transition, there are some superlattice reflections are seen here, which confirms that there is a structural transition which has happened in this one, and this is attributed to the CDW transitions here. Okay, so the other interesting phenomena that we have observed is that in the case of Hall effect, we see this kind of step-like feature, which is attributed to quantum Hall effect in this case, because this is a bulk system. So in spite of the fact that it is a bulk system, because typically the quantum Hall effect is observed in two-dimensional cases, two-dimensional samples, but here we have also observed it as a three-dimensional sample, and whenever there is a plateau here, the electrical resistance is decreasing here. You can see the minima in the electrical resistivity. So this, of course, the filling factor is very high here. So we need to apply a huge magnetic field to check actually whether they are really a quantized Hall steps. So to summarize, single crystals can be grown by a variety of methods. Here I have explained about these two high melting samples like molybdenum disilicide, and which has a high melting point that can be grown by Zuchralski method, and the pnictides where the antimony and arsenic compounds can be grown by this flux growth method. And yeah, that's it. Thank you very much for your attention.
We have time for questions. Thank you for finishing on great time. We have time for questions. Yeah. Thank you for the talk.
I was just curious about this structural transition in this
Copper
copper
for arsenic.
example. So in the you said this has this R3 bar N
Yeah.
phase group. Is there is the mirror symmetry still existing below the transition?
So it's a kind of, it goes to a monoclinic because it goes to a monoclinic or a triclinic service. But we have not actually determined what is the structure, but there is a structural transition. That's it.
Because this tantalum disulfide and the diselenide ones, there the CDW transition once it takes place, they have this mirror symmetry removal.
Okay, okay. But actually here we don't know what exactly, which structure it goes to.
Another big question I just wanted to ask is that I understand this process of this thing, but then in some cases you might end up with twinnings and domains of the crystals. So how do you kind of isolate them or avoid them? I mean,
See,
apart from the Naue and cutting.
See, one way is that we have to use a temperature gradient in your furnace during the growth. So this is the thing that we have done long back on YBCO single crystals that is prone for twinning. You know, the tetragonal to orthorhombic crystal structure transition leads to this kind of twinning. So one can, either you can do a temperature inside the furnace, you can have a temperature gradient in such a way that this twinning can be removed. But that's a very difficult process. You need to optimize the growth conditions multiple times. The other one is that you apply some pressure or something like that post growth. After the growth, you apply some kind of strain to that to remove the twinning.
So
Yeah, just one small question that in CTW transition, in magnetization, doesn't you observe any broad feature, broad anomaly?
So we have not done magnetization here. It is only the electrical resistivity and the heat capacity, which shows a change in the electrical resistivity there is a drop, and the heat capacity there is a peak. In magnetization, we have not seen any change there.
Are there very interesting talk. So I was just wondering, in the phase diagram that you showed, so how do you decide? As you said, the eutectic point is one where you usually like the flux to be in the coppers and antimonies.
Oh, so this is the eutectic point. So suppose if I want to grow this silver neodymium, so inside this region, you have liquid plus solid. The solid will have this composition. The liquid will have composition close to this eutectic point. So if I want to grow this silver neodymium, I take this composition as an excess composition along with this silver neodymium, and I heat up to 1050. When I enter into this region by temperature wise, because this is a temperature scale, when I enter into this region, the silver neodymium, which has to be in solid phase, it will crystallize. So if I use this as a flux, I can get the single crystals of silver. So if I go this side, it may, I mean, I will end up with neodymium single crystals.
So usually the top of the thing is the one which is the corresponding.
So this is a congruent melting composition. That means if I have the facility to grow this crystal by Czochralski method, I can melt it and then I can directly grow. But if I say, for example, if molybdenum silicide, it here, if I want to use this as a flux, I can use this composition of silicon, around 95% of silicon and 5 mole percent of molybdenum. And I can, when I enter into this one, molybdenum silicide will crystallize. But you see the temperature, it's about 1400 degrees centigrade. I cannot even use quartz tubes to grow these crystals. So you need to check the temperature also. So anything if you see like this, it has a liquid plus solid composition. The solid will have this composition, the liquid will have this composition.
I have a quick question
Yes.
related to the structural transition again. You also mentioned it is CDW.
Yes, yes, yes.
So, structure, how do you characterize that this is a CDW? It's not a simple structural transition.
Okay, so the structural transition we have observed just by, because heat capacity is also showing a huge peak.
So that happens for any structural
So,
transition, right?
See, at that temperature, it's about 52 Kelvin. So you will see only a subtle transition if there is a structural transition. But this shows a sharp peak. So that gives some sort of evidence. But we need to do RPES to confirm this CDW nature.
And is there anything to do with the resistance also showing the change? That means hard surface is also some sort of having a change in terms of density that can be also linked to.
Probably. So because this resistivity shows a sharp drop. Typically in a CDW system, I would expect the resistivity to go up because of the gap opening. But here it shows a sharp drop. So that's why I brought the analogy of tantalum diselenide, where that also shows a decrease in the electrical resistivity during at the CDW transition. So, but this has to be explored. What is the nature?
Okay, so let's thank the speaker for a very nice talk.